Okay, let's look at the normal distribution, also known as the Gaussian distribution. The normal distribution is an extremely important continuous probability distribution. Remember, this is for continuous probability distribution. It arises very frequently in theory and practice. Here I've hypothetically plotted out what is approximately the distribution of the height of adult Malaysian males. So please mind my drawing, I'm not an artist. And this is what we see here is a binomial distribution. Usually binomial distribution looks like a bell shape. Okay, and this is what we see here. Okay, this is our variable down here. This is the height, this is the variable, and f of x here, okay, of fx is what we call the probability density function, which gives the height, okay, which gives the height of the curve at point x. So here's the equation for the probability density function of the normal distribution. We are not going to be working with this directly very often, but there's a few points we should note. First of all, if the random variable x has a normal distribution, then it can take on any finite value. Okay, if the I repeat, if the random variable x has a normal distribution, then it can take any of finite value. There are two parameters to this distribution. Okay, first is the mu. Again, mu is the mean uh, of the distribution, and the mean, same thing, can take any infinite value as well. So it can be mu up to infinity. Okay, sigma is the standard deviation, and of course sigma squared is the variance. Sigma has to be some positive value, okay, and of course sigma squared will have same thing, have to be some positive values as well. Here's a normal distribution plotted out. Mu here is the mean is also right smack dab in the middle of the distribution. The distribution is symmetric at about mu. So mu represents the mean of the probability distribution, and it's also the median of the probability distribution. Now let's try and get some perspective for what sigma represent. Here I've plotted in one standard deviation below the mean, and one standard deviation above the mean. And as well as we'll see a little bit later on, this area, okay, this area, okay, uh, between one standard deviation to another standard to the next standard deviation, okay, below to one standard deviation above is approximately, okay, 0.68, okay, or 68% of the area lies within one standard deviation of the mean. And here I've plotted I've plotted in mu minus 2 standard deviation and 2 plus 2 standard deviation, and approximately this area between these two mean is equals to 95% or 0.95. Since this area is 95% of the area lies within two standard deviations of the mean if we double the standard deviation. What if we triple the standard deviation here? Okay, here we can say that between these two standard deviation there is a probability of 99.7% or 0.997 of the area lies within 3 standard deviation of the mean. Here's another plot to give us a little perspective on what sigma represents. Over here, the blue line represents a normal distribution with a standard deviation of sigma 1. Okay, and this red curve represents a normal distribution with the standard deviation of sigma, this is sigma 1 and this is sigma 2. Okay, the blue curve is sigma 2 and the red curve is sigma 1. Here, sigma 2 actually is double of sigma 1. Okay, so the standard deviation on the blue curve is double the standard deviation of the red curve. And we can see here that when the standard deviation is greater, when we have more standard deviation, when we have the standard deviation is become bigger, the peak become lower. So they will reduce the peak, but the tail area become larger. So tail become larger, okay, and the peak getting shorter or lower. There are an infinite number of different normal distributions corresponding to all the different possible values for mu and sigma. If x is a random variable that has a normal distribution with mean mu and variance sigma squared, we write this as the random variable x is distributed normally with a mean of mu and a standard deviation of sigma. Be a bit careful here, as different sources or books can have the second term here representing the variance as sigma squared. I have here the second term is representing the standard deviation. Sometimes the use of variance is more popular, but I just want to stick with the standard deviation. By the definition, the standard normal distribution is a normal distribution with the mean of 0 and the standard deviation of 1. We often represent random variables that have the standard normal distribution. Okay, that have the standard with the letter Z. Okay, and this we might say if Z has a normal distribution, we might write this as Z is distributed normally with a mean of 0 and standard deviation of 1. And if standard deviation is equal to 1, of course, sigma squared, the variance is 1 as well. We also very often need to find areas under the standard normal deviation curve. Okay, probabilities are simply areas under the curve. And very often, the question of interest involves finding a probability. Okay? Finding probabilities and percentiles for the normal distribution requires integrating the probability density function. There is not a closed form solution, and it must be integrated numerically. Fortunately for us, we are going to use a standard normal table to actually find this value, okay, the probability of these values in practice. Here we are looking, we are going to look at finding areas under the standard normal curve using the standard normal table, and bear in mind that there are a couple of different types of tables that we commonly run into. For this class, you can turn to page 13 of your statistical tables book and look at table 3. Here we look at a table that gives the area to the right of Z. Okay, in other words, things that look like this. Okay, suppose that Z is a random variable with a standard normal distribution, and we want to know the probability that Z takes on a value more than 1.43. First of all, note that this is exactly the same if we were to say the probability that Z is more than or equal to 1.43. Okay, because the probability of Z is equal to 1.43 is 0. That is a continuous random variable, and for continuous random variables, the probability that are exactly equal to any value is 0. So whether I say less than or less than equal to, we get the same answer. This little bell shaped and has 0 in the middle. Okay, it is symmetric about 0, and the area under the entire curve, okay, and the area under the entire curve is equal to 1. Okay, let's make our own bell shape here. Okay, so the symmetric of 0 here will make a symmetric, and 1.43 will be somewhere here. And we got the probabilities from areas under the curve. The probability that Z is more than 1.43 is simply the area under the curve 1.4 under the curve to the right of 1.43. So we want to find the probability of an area here. To find that area requires calculus and integration and the sort of thing but it needs to be done numerically, and the results have been summarized in these tables. Okay, this particular type of tables gives the area to the right to the curve, and so if we go down here, we found that this is a Z here. Okay, this formula is for Z, and so if we go down here, we found 1.4 here, and this is the first decimal place of Z given, and then the second decimal place is given across this top. So 1.43, we find where this column intersect with that row. Say 1.43 here. So where's the intersection? It will be 0.764, and we find that there is 0.764. In other words, this area, okay, is 0.764, and that is precisely what we are going to find here. Oh, sorry, not 0.764, 0.0764. I'm sorry for making mistake here. We already know that P Z more than 1.43 is equal to 0.0764. Now, what happened if you want to know that P is less than 1.43? So basically, we want to find the area. If this is 1.4, Z here is 1.43, you want to find the area to the left of Z. So which means that you want to find this area. Remember that the whole area of under the curve is equal to 1. So if we want to find the value or probability to the left, so what we need to do is just subtract this with the p z above 1.43, which we got it as 0.0764. So 1 minus 0.064 is equals to 0 sorry 0.9236. So this is the probability of to finding this area. Another type of question that always been asked is to find the probability in between two values of z. And for this instance, we want to find the value of the probability of the area in between negative 1.34 to 0.62. And then if we make our own bell curve here, we know that negative 1 point, this is 0, right? So negative 1.34 is somewhere here, negative 1.34, and 0.62 is somewhere here. So we want to find the area in between, the probability to find chances or probability in this between these two value 1.34 and 1.62. Note that when we want to use our table, they always give you a positive number. So how you want to find a value of z if you have a negative integer like this, 1.34? Okay, now let's work on this 1.3 negative 1, the value of a probability of 1.34 first. Remember that we want any values that we have is on the right of the values of the probability. So we look at this, we draw another curve, and then we know that 1.34, negative 1.34 is somewhere here. So note also that a normal distribution is always symmetrical. So which means that the value here is symmetrical, is in mirror with 1.34 here. What does it means that the value is in 1.34 in the table will give you the probability to find this area. So let's say we work on this one, 1.34. This is 1.3 and 4 will give you the probability is equal to 0.0901. So because this is a mirror image, so the value of 1.34 on the left side here is similar to the value on the right side of 1.34 if the negative. So the same value will, the probability of negative 1.34 is similar to the 1.34, which means that the probability of negative 1.34 is equals to 0.0901. So again, that we know that probability of z is less than negative 1.34 is equals to 0.0901, which means that in this one if this is negative 1.34, we have the values of here negative 0.0901, and then what we want is the value of to the right of negative 1.34, because here we want to 0.62, so we want to have the value on the right side. So this value only give you the value of the left side, so the value probability of right side will be 1 minus 0.0901, which equals to okay, which equals to 0.9099. So this value, the probability of this value represent the whole area until the end of the tail. But we want to delimit the area until 0.62 here. So we want to find this area. So what we need to do is discard this area. So what we will do next is to find the probability of Z is more than 0.62. Okay, the probability of Z is more than 0.62 is 0.6. If we find Z is 0.62, which give you 0.2709. So this only the area of the right side of 0.62, and then because we want to find this area, what we need to do is to deduct probability of whole area from the right side of negative 1.34 with 0.62. Then you can get the area. So now we know that the Z, the probability, so we need to probability of Z less than 1 point more sorry, the probability of Z more than 1.34, okay, divided by minus probability of Z more than 0.62, then you can get this probability of negative 1.34 less or equal of Z less than equal of 0.62, which in this case 0.9099 subtract of 0.2709. Let me clear a little bit here. Okay, so the probability will be okay 0.9099 minus 0.2709 is equals to 0.639. This is the probability. This is equal 0.639. Okay, next let's look at standardizing normally distributed random variables. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. The standard normal distribution comes up frequently in probability calculations and statistical inferences. Well, we will soon see that we can convert a random variable having a normal distribution with any mean and standard deviation into a random variable that has the standard normal distribution. This will help with some probability calculations. We deal with the standard normal distribution very often in statistics. Just recall that suppose X is normally distributed is a normally distributed random variable with a mean of mu and the standard deviation of sigma. We can write this as X is distributed normally with a mean of mu and a standard deviation of sigma. Now we are going to standardize this. We are going to turn this into a random variable that has the standard normal distribution by using a basic linear transformation. Basic linear transformation here. The random variable X of a mean has a mean of mu. So X is equal to mu. So if we were to subtract X to mu, then this quantity is going to have a mean of 0. And if we divide by the standard deviation or sigma, then we are forcing this quantity to have the standard deviation of 1. This is a linear transformation on the random variable x, and the transformed variable has a mean of 0 and a standard deviation of 1. I'm going to call this as z is distributed normally. Okay, z is distributed normally with the mean of 0 and the standard deviation of 1. Note that by subtracting the mean and dividing by the standard deviation, we are forcing the random variable to have a mean of 0 and standard deviation of 1. This doesn't change the shape of the distribution. Here z is only normal because x is normal. But if x has had a different distribution, then z would not be normally distributed. Now let's take a look at how we might use this in probability calculations. So a lifetime of an electrical component is known to be a normal distribution with a mean of 2000 hours and standard deviation of 200 hours. What is the probability of having a component with a lifetime between 2000 to 2400 hours? So we have a normal distribution is normally distributed here, and then the mean for this one is 2000, and they want to know that 2400, so they have a standard deviation of 200 hours. So here they want to know what is the probability of having a component with a lifetime between these 2000 and 2400 hours. So now we want to find the z. Okay, you know that the z is mean minus mu divided by standard deviation. So we have two types of z here. We have the 2000 and the 2400. So the first z is, we know that we want to find this value here. So this x will be 2000, and eventually this is also the mean. So mean is 2000 and the standard deviation equals to 200. So z1 is equal to 0. While z2 here, okay, change the color a bit. So z2 here is 2400 minus 2000. So x is 2400 and mu is constant is 2000 divided by 200, and this will give you the value of 2. So therefore z1 here is equal to 0 while z2 is equals to 2. And if we go to the probability table and we look at, again we look at the table, we know that the z2 here more than 2 is equal, the probability of z2 is equal to 0.02275, which is the area of this area, and then we want to know this between area. So we also note that the probability is a symmetrical of 0 here. So the probability, the total probability will be 1. So 0 here is if z is 0, which means exactly of the mean. So the area on the right side will be 0.5, because 1 divided by 2 is equals to 0.5. So if we want to find the area of this area, okay, you want to find this area, so you need to find the probability here. The probability to find the component on the right side is 0.5, and here it will be 0.02275. Therefore what we will have here is just subtracting 0.5 minus 0.02275, which will give you 0.47725. So these are the probability of having a component of lifetime between 2000 to 2400 hours. So here's the summary of what we have calculated before. So you can do this and you can find with the same principle of any value of z. So probably this is will be negative value of z on it. So we want to find this area. So these are some of the application on how to find the probability under the normal, the probability of any values under the normal curve, as we discussed in this continuous distribution or the not continuous normal distribution.